Hello, rock stars, and welcome to Chapter 3, Section 1. From now on, the lectures, where appropriate, will be broken into small sections. This one is for Chapter 3, Section 1. Not all chapter sections will have a lecture. For example, Chapter 3, Section 2 is pretty simple, so you're just going to read the chapter, do the simulations or visualizations, and answer the questions in the study sheet there. Usually I'll remind you of the key ideas and the vocabulary. This, by the way, is being recorded the 2nd of October, 2012. It is a beautiful morning, but it's still warm. So if you hear a noise in the background, that's the fan running. Maps. Models of a spherical Earth. There are problems with maps. They have distortions, but we do what we can. Keywords: map, two-dimensional representation of a three-dimensional planet. Cartographer, person who makes maps, comes from Greek harte, which means map or paper, and grapher, to write. So writing a map, a projection. I'll show you what that means. Hemisphere, equator, prime meridian. Latitudes help you go north and south. Longitudes help you go east and west. And map scale. Okay, here's a projection. And here's the problem with projections. The Earth is roughly spherical. Let's say you got bored in your earth science class. Not like this class. It was a normal class and you got bored. This one's too exciting. And you had a globe and you started peeling the paper off the globe because you knew your teacher needed a map. And you thought you would be nice. So you pull these little sections, like sections of an orange or a tangerine, off the globe and you paste them onto the wall. Would it turn out like this? Not at all, because there would be big sections that would be missing. You would see the paint of the wallboard through. This is the problem with maps. You're trying to take a three-dimensional object and project it into a two-dimensional flat map. It doesn't work well. And when we say project, we really do mean project. Here you have to use your imagination. Pretend you're watching Channel 8 as a kid again. There's a light bulb inside this globe. This globe is transparent, and somebody has drawn all the continents onto the transparent globe. You then take a piece of acetate, like clear plastic, and make a cylinder around the globe. You turn on a light bulb inside this globe, and you project these lines out onto this acetate. You get your magic marker, and you start drawing where the lines are. You unwrap this acetate, and this is what you're going to get. It really is a projection. And this is how it's done, at least mathematically. Computers do it automatically. You don't need a light bulb anymore. But you can see a problem. The only place where the cylinder is touching the globe is at the equator. That's the only place this will be truly accurate. As you head away north or south from the equator, the projection becomes less accurate. In fact, if you're a polar bear, find where you are on this map. Okay, so they're up in this part of the world, at least for now. But Santa Claus, he's not on here. The very South Pole, anti-Santa Claus, he's not on here. Take a look at Greenland on the sphere, the globe. It is about the size of Alaska, maybe 1.5 times the size. Take a look at Greenland on our map. Anything moving away from the equator gets continuously larger and larger. This is a problem with all projections. The Mercator projection is great for true direction, north, south, east, west, in a straight line. But distance near the poles gets distorted. So let's try something else. Let's try a mnemonic projection. A mnemonic projection is where you put a plate, a clear piece of acetate, onto an area and project upwards. This works well for small areas, and it's great near the center point, but as you go out, not very good. Here's the Yucatan Peninsula. Here's the Isthmus of Mexico. Take a look how fat the isthmus gets on this projection. Weird. So we use this, a polyconic projection. You take an ice cream cone, you can make it narrower or fatter depending on what you need to do. You lay it over the globe and you project outwards. This works really well for areas between, say, 60 and 30 degrees north of the equator, the mid-latitudes. This is what we use for topographic maps. Now, latitudes and longitudes. If you divide the Earth into two spheres, hemi, half, sphere, a ball, half of a ball, you got the north and the south hemisphere. The line that divides them into equal parts is the equator. Okay, the equator. We call that 0 degrees, north or south latitude. Going north, you can go all the way up to 90 degrees or down to 90 degrees south. There's 30 north, 60 north, 90 north, 30 south, 60 south, 90 south. It's pretty easy. I like to think of it this way. It's like, well, like a ladder. That's why it's called latitudes. Here are the rungs of the ladder. You can go up or down, north or south on these rungs. Yes, the rungs run left and right or east and west, but they help you go up and down, like the rungs of a ladder. Longitudes are a little bit more abstract. You can see why we start measuring from the equator, but for longitudes, we could start measuring from anywhere. In fact, I suspect that there were at least a couple of civilizations that started creating maps before the British did. But the British won out, and we start measuring from an arbitrary line, one that runs through Greenwich, England, which, by the way, looks like Greenwich, England. Going this direction, all the way to the back side of the world, you can go 180 degrees. So this is said to be west longitude. Going this direction, said to be going east longitude. It's pretty simple. I think it would have been a lot more logical just to say we're going to start measuring from here and go 30, 60, 90, imagine the back side here, 120, 150, 180, 210, 240, 270, 300, 330, and 360, or 0. That would have made a lot more sense, but, well, it was a long time ago. People weren't sensible. Now, as far as a scale goes, if you made a map of your school and you made it at a scale of 1:1, or what we call a scale of 1 to 1, that means that 1 inch on your map would be equal to 1 inch on your school grounds. That would be a problem because the map would be the same size as the school. What could you do to make it smaller? Well, use a scale of 1 to 2. That means from left to right, your paper would be only half as big as your school, and from top to bottom, your paper would be only half as big as your school, which is a little weird because it ends up being 1/4 the real size of your school, half times half. That still won't work. To make a map of your school, you probably need something like 1 to 1,000. To make a map of Maricopa County, the county in which Phoenix resides, a map of 1 to 24,000. That means that 1 inch on the paper equals 24,000 inches on the real world. Or 1 inch equals 2,000 feet, because there are 2,000 feet in 24,000 inches. We can also have a graphic scale. This graphic scale, 1 mile, 0, and then another mile broken into sections. So this entire graphic representation is 2 miles long. Here is a graphic representation in feet, and here's one in kilometers. Now, a note on big and small scales. If you want a map of the entire world, you may want a scale of 1 to 1 million. If you want a map of your neighborhood, you may want one of 1 to 500. If this number is large, like 1 to 1 million, that means you have shrunk down the map because this number is large. If this number is small, like 1 to 1, that means your map is going to be large, which I know is a little bit weird. Let's do one more thing and then practice maps. This is a compass rose. By convention, north on a map is always up, east to the right, south to the bottom, and west to the left. In between north and east is northeast. Between east and south, southeast, southwest, and northwest. And then to be even more specific, between northeast and northwest is north-northeast. Between northeast and east is east-northeast. And you get the idea. Okay. Here's a Mercator projection. Let's try some latitude problems. Folks, what is the latitude of that green dot? You have to state the number and the direction, either north or south. In this case, the green dot is south 30 degrees, so we say 30 degrees south. Let's try something else. Name 3 continents that the 30 degrees south line passes through. 30 degrees south line. And it goes through South America, Africa, and Australia, mate. Next one. Here are longitudes. Notice that longitudes are always the entire way around half the planet. They always go from the south to the North Pole. By comparison, let me go back a little bit. Latitudes don't always have the same length. The equator is 24,000 miles around. But as you go north or south, the length of each longitude line becomes shorter and shorter. In fact, at the North Pole, you could walk around 90 degrees north latitude simply by spinning. So let's say you had an evil online earth science teacher who says, "I'm mad at you. You now have to walk around an entire latitude of the earth." You laugh because you know a quick way to get around this. All you have to do is fly to the North Pole, spin around in a circle, come back, and laugh because you're smart. Maybe. Okay, let's try this. What is the longitude of this green dot? In other words, how far east or west of the place that we decided to start measuring from is this dot? Well, it's on the west longitudes, and it is 30 degrees west. Let's put the two together. What are the latitude and longitude of this blue dot? First, latitude. It is 15, 30, 45, 60 degrees south, and 15 degrees west. Let's try this blue dot. It is 45 degrees north and 175 degrees east. That's it, rock stars. Go work on your study sheets.